Welcome. This is the first part of a series of talks on medical image reconstruction using deep learning. Primarily, I'll use the example of PET imaging, but the methods are applicable to many different medical imaging modalities, and I will include an occasional example for MR and for CT. So in conventional PET image reconstruction, we have a radiotracer distribution, which I'll be calling a vector T, inside the field of view. Now obviously I'm using a discrete approximation here, but you get the idea. I'm just saying that there is a ground truth unknown radiotracer concentration inside the PET scanner field of view. And what is happening is that we collect back-to-back photon pairs and we have Poisson distributed noisy data, which I'll be calling a vector M, and this is just a simple example 2D sinogram, which is one noisy realization of what we might have obtained from a scan of that ground truth radiotracer distribution. I'm just using a Shepp-Logan phantom there for simplicity of this example. And then what we're doing in reconstruction is saying, well, what are the object representation parameters? In other words, what is that vector X, that set of coefficients for each of the pixels? In other words, just the list of numbers that makes up that image in the reconstruction. How do we go about finding that? So we start off with a guess of what the vector X is. It would just be uniform valued typically, and that's our current estimate, our current reconstruction. And what we'll be doing is, for example, applying a radon transform forward model along with many other components according to your system matrix representing your scanner, modeling your scanner. So that would include positron range, it would include effects such as scatter, which is what I'm showing here, that we could have a line interval forward model. We could include attenuation, normalization, add-on, scatter and randoms in the context of PET. What we have then is a model of our measured data, model of the mean of the measured data for a given estimate of our radiotracer concentration. So initially this will often be uniform, and we forward model it to predict what the mean of the measured data would have been had this been the actual object inside the field of view. Whereas all that we've got to go on from our acquisition is just the measured data vector M. And so what we do is just compare this mean of the measured data, our model of the mean, according to our current reconstructed estimate X, compare that with the actual realization of data that we acquired M, and then we use a Poisson noise model typically, and use that as a way of measuring the level of agreement between the measured data and our model of the mean of that data. So this is just a distance metric between our model AX and our measurement M, and that's what we call an objective function. So in MR that would be least squares quite typically, and in PET it's nearly always a Kullback-Leibler divergence measure, basically a Poisson log likelihood measure. So what we do is we do an iterative algorithm to iteratively improve the estimate of the vector X. And so the well-known algorithm for doing that would be MLEM or OSEM, forward project our estimate xn, add on scatter and randoms background, compared to the measured data, back project, multiply, normalize by the sensitivity image, and we just iteratively update in that way. So the problems with this conventional approach to image reconstruction is that we are fitting our parameters X, our vector of coefficients for those basis functions, those pixels, we're fitting that to a noisy data vector M, and so as a result we get noisy reconstructions X. So that's problem number one with conventional reconstruction. Problem number two is that if we're not happy with the noisy data fitting, then if we go about regularizing or compensating for noise, which is what we often do with MAP-EM reconstruction, if we go about that, we're then stuck with the problem of, well, how strong should our noise compensation or our regularization be? In other words, what's the hyperparameter beta, just by basically having a penalty term here for the agreement between our model and the data. We don't want it to fit too closely, and so this is why we add on this penalty for when X in some way doesn't agree with the kind of images that we like to see. So in other words, if X is noisy, this would be large, and it would discourage the fit from being too close. But the problem with this, as I was saying, is that we don't know how strong to make that, And furthermore, we don't even know what kind of penalty function R to use. At least with the distance, we could use the Poisson log likelihood, which is a very well-founded choice based on the Poisson stats of the measured data. But to go about claiming we know what the image should look like for any given patient, we're not in a strong position to choose the correct kind of prior function. In other words, we're not in a good position to talk about what is the probability of a given image X. So what is it about the machine learning approach that is different to conventional reconstruction? Well, this slide is trying to capture the basic idea. And you'll notice that what I've got here are examples of the ground truth radio tracer distributions, 3 different examples. And remember in that earlier talk through of reconstruction, we had that ground truth distribution T, but in no way did it ever enter into the picture of our conventional image reconstruction. Whereas with machine learning, what we're going to be doing, as emphasized here, is actually accounting for a ground truth or high quality reference when we do the reconstruction. So what I'm showing here then are ground truth distributions, different examples, just 3 different examples of a radio tracer distribution. They're not very realistic, it's just an illustration here. And we're relating them to the measured data. So imagine we had 3 different distributions, put them inside the PET scanner, and imagine we got 3 different sets of measured data. I'm just showing them as 2D sinograms in this example. Now with machine learning, what we're going to do is try and find a mapping or a link, an operator that will take us from the measured data back to the ground truth. So what we're trying to do then is find a mapping, an operator F, which when operating on a given measured data set M, parameterized, and the operator is going to be parameterized by some vector of parameters theta hat. What we need is some mapping that when you supply it with measured data will give us an estimate of what the underlying ground truth was. So this is very much like doing a regression problem. We've often done least squares fitting. We have X and Y values. And what you do is you use the X and Y values to fit a line, for example. Now here with this approach here, I'm just extending that to a very high dimensional vector T here and a high dimensional vector M. But I'm still using initially a simple linear mapping, a matrix vector multiplication. And what we're going to do is try and find the parameters theta of this linear mapping that minimizes the distance between each of these pairs. So in other words, can we find that line that best relates all of our example pairs of data? And these are what are called training data pairs. This is our training set. So on this slide here, I'm only showing 3 training pairs, and we're going to use them in a supervised learning framework whereby we're finding the parameters theta such that for each of the capital N training pairs in our training set, we want to therefore minimize this distance, which in machine learning is often called a loss function. We're trying to measure the level of agreement between our inference of the reconstruction. So that's this mapping operating on a measured data vector M. So that's trying to infer what the ground truth is. And so we're just trying to minimize the discrepancy between our inference and our actual target data, our label, if you like. And again, the idea being that when we've got unseen new data from a new patient being scanned, we can just run that through our mapping and make an inference of what the ground truth was. Now remember, in conventional reconstruction, what we're doing is just fitting noisy data and maybe compensating for noise. Here, we're learning a mapping between noisy measured data and a high quality reference, such that when we put noisy data in, we infer a high quality reference straight away. Okay, so let's just rearrange that to see what a linear mapping would look like. Well, for something like a PET with a linear mapping, it would just be a matrix vector multiplication where we have the measured sinogram in a vector, just a stack of all the values in the sinogram here, and would have some matrix F, for example, for that linear mapping, and would want that to be approximately equal to that ground truth T, which again could have been found through use of simulations or through use of higher quality reference data. And the idea then is to learn that matrix F by training pairs. And for this example of a linear mapping of just one huge matrix F, this would correspond in machine learning language to a fully connected layer or a linear layer or a dense layer of an artificial neural network. And for PET, we can well imagine that such a linear mapping would exist. We know that the filtered back projection algorithm is a purely linear operator, and so it stands to reason that a linear operator should exist that can take us from measured sinograms to an estimate of the ground truth radio tracer distribution. And in fact, as we'll see later on, filtered back projection is of course a cascade of linear mappings, and that's where we get the idea of depth, a sequence of processes that are being done in deep learning. And so with machine learning then, what would be the key difference compared to, say, a filtered back projection linear mapping? Well, first of all, machine learning would not only be learning the inverse mapping here, but it would also at the same time be directly accounting for the presence of noise in the measured data. It would be, if you like, trying to find noise compensation within that linear operator so as to best match the ground truth. So that's a big advantage already. And also it would be learning effectively as best as possible. It's quite difficult with just a linear mapping, but it would be learning also to only deliver reconstructed images that are members of the manifold of PET images. Now there is a big problem here I'd like to point out, of course, is that for 2D PET this might be feasible, but for the case of 3D reconstruction from hundreds of sinograms into tens of millions of voxels or pixels, we could be dealing with upwards of 1 trillion parameters, in fact probably a lot more than that, trillions of parameters that would need to be estimated. So clearly this is going to be quite a challenge if we were to just naively try and find some one single matrix F to do this reconstruction. Okay, so let's take a look at the link with filtered back projection. So with filtered back projection, we could view that as a deep network as follows. So here is first of all our sinogram shown as a vector here in this kind of rectangle format. And I'm showing filtered back projection as just one big linear operator taking us to another vector. This time it's just a list of pixel values in the reconstructed image. Now, of course, that process of filtered back projection could in fact be decomposed into 2 stages. The first stage is a convolution of each of the rows of the sinogram, each of the view angles of the sinogram could be convolved with some kind of reconstruction kernel. And once we've done the filtering of the sinogram, we can just back project all the view angles to get a reconstructed image. Now at this point I want to point out that this was in fact one of the early pieces of work for machine learning for the case of image reconstruction, in this case for SPECT imaging, where Floyd put forward an artificial neural network for SPECT image reconstruction, and this is what he did. He just learned one single but very large convolution kernel that could be applied to each of the rows of the sinogram, such that once you've convolved each of the rows of the sinogram, you can then back project that sinogram to get a reconstructed image. And so what he did was, I think he used point source data to learn what that convolution kernel would need to be in order to successfully filter a sinogram and then back project it to get a reconstruction of a point source. And so what he would have done there was just optimize, if you like, all the values of a convolution kernel. So this is rather old notation for an ANN, an artificial neural network. We'll be going on to more modern deep learning notation presently. But just to show that this is effectively the architecture proposed in that 1991 TMI paper, or it was quite a short article, where in fact he was just looking at the mean square error loss between his current reconstruction based on a current estimate of the kernel parameters and the known target, which I think was for reconstruction of a point source image. And so he successfully managed to do reconstructions from learned convolution kernels. So that was a very early piece of work, introducing machine learning into emission tomography image reconstruction. And here I just want to show a fact that, of course, that linear mapping of filterback projection could be decomposed even more into various stages. And this is where, again, we can view it as a deep network. So in other words, we would often be Fourier transforming each one of the projection angles there. So that's like an encoder, an analysis operation. We could then do some processing, some modification of those frequencies. So that would typically be a ramp filter or some kind of a smooth version. Some apodized ramp filter could be used. And then we could do an inverse Fourier transform to decode that back to the sinogram domain, and then go ahead with a back projection to get a reconstruction. So here, these stages are all typically, of course, just pre-chosen and fixed analytically and by empirical choice in terms of any apodization of the ramp filter. Whereas with the machine learning framework, ultimately, we want to be learning as much of this as possible, although of course that's an open question as to how much of it we should learn, how much of it we should rely on our prior knowledge. And I think where we're going in the field is to combine as sure knowledge of stats like Poisson distribution, as sure knowledge of the imaging physics like the system model, combine that with aspects that we don't know, such as what is the realistic probability of a given PET image, for example. But anyway, the point here is that we could learn, of course, any and every part of this mapping if we were so motivated to do. But just a reminder then of just that simple linear mapping, taking us from a sinogram to an image. If this were a 3D problem, it's going to be a massive problem to solve if we wanted to learn the entirety of the process. It's a massive problem to solve, especially in 3D. And that therefore raises the question, are there more parameter efficient mappings available? In other words, here, if we need to go from a 3D set of sinograms to a 3D reconstructed image, if we need 1 trillion parameters, that's clearly not viable. Are there more computationally efficient ways of doing it? And the answer, of course, is yes. And that's why in the next part of this talk, I'll be dealing with image-to-image mappings through the process of convolution, leading up to convolutional neural networks, which in turn will then lead us into how we go about actually finding non-linear mappings from sinograms to images, which would correspond to direct image reconstruction, deep learned architectures. Okay, so the simplification at this stage is that we're going to go from an image to an image. And in particular, though, it's going to be a noisy image or some image that's been degraded in some way. And we want to map that to a high quality reference. And remember, that's at the heart of machine learning and deep learning, is to go from our noisy acquired data, our suboptimal data, and map that to a better quality ground truth reference of some sort. So we've already seen that a large matrix F could do a mapping from one image to another, or from a sinogram to an image. But here, we're just now going to use image to image and get away, therefore, with just a convolution. So what would that look like? So here is our measured data vector, now just a noisy image. And the matrix F, before it was fully general, now if it's a circulant matrix, a convolution matrix, all we'd do, for example, I'm just showing you a simple convolution kernel, 3 by 3 here. All we'd do is just list that as a row vector in the first row of the matrix and just duplicate it with different shifts all the way down all of the rows of that matrix F, or indeed, as I prefer, actually, we could consider it as columns with just shifted copies of that kernel. And the point being, therefore, with just 9 parameters, we have massively simplified a large linear mapping which will deliver an output vector, in this case, of the same size as the input vector. So here this input should be the same size as the output. So let's see how that would work in the context of machine learning then. How could we learn some kind of optimal kernel? Well, first of all then, if we had some noisy image input vector x, just shown again by that vertical rectangle as a vector, if we didn't learn anything in the kernel, if we just had it as some single delta function, just that there was a 1 and then zeros around the outside, then the input, of course, would directly map to the output. But the point is, I'm now beginning to introduce some notation for deep architectures where we've got a vector going to a vector via this operator here, this blue arrow showing a 3x3 kernel, and that would correspond to 9 parameters, which we are going to learn. Now, the idea is, as we know, that we're going to want to map our input to a high quality reference or target. So if we go about modifying the parameters here according to the target, well, how do we do that? First of all, then, the fact we've got an input and a desired target means we have training data for supervised learning. And what we can do then is go about minimizing a loss function, which would be a way of describing the discrepancy between an output for a given kernel and our desired target t. So if t is our target, y is our current output for a given parameterization of the kernel, then we can say how good that kernel is. And the idea will be to modify the values in this kernel such that the output here best matches the target according to that least squares cost function, or indeed mean square error loss function, the objective function if you like. And that could be done via optimizers such as gradient descent or stochastic gradient descent. These are optimizers that are going to change the values inside this kernel here such that the output matches the target as best as possible. And that's exactly what I'm showing here. You'll see that first of all it looks noisy, and then once we've done the optimization here, this was actually just a methodical search through all the values in this simple kernel. By doing that search, look at the difference. We've now found an optimized smoothing kernel which will take a noisy image and optimally smooth it, given just the limitations of that simple model, smooth it in the best possible way to get it to agree with the target. So the point of convolution is that it can not only just smooth images to reduce noise like we've looked at, but it can also sharpen images, do resolution recovery as well. So what would that look like if we do the same process of putting an input in? This is our training data. Here's an example, and here's the target for that example. How do we, what are the parameters that we find when we optimize now even a 5x5 convolution kernel? Well, what we see is that we get a convolution kernel now with negative values within it, which is what we'd need for edge enhancement, for recovery of high spatial frequencies. And you can see that this blurred input image has now been resolution recovered to some extent within the limitations of a mere 5x5 kernel. We have learned the kernel that we need to go from a blurry image to a sharpened image by trying to minimize, find the parameters that minimize the discrepancy between y and the target t as captured in the mean square error loss function. Okay, so that's just a little idea of the power of just one tiny little convolution kernel. Also though, these kernels, when used with non-linearities, when used with, for example, what are called activation functions, effectively the one you need to really know about would be the ReLU function, which we'll touch on in a moment. These convolution processes can also act as feature detectors, which is going to be a very crucial concept to understand. So now if we've got some brain image with some feature here, this could be some lesion, for example, what we can do, now I'm going up to a 7x7 kernel. Now here I'm not learning the kernel, I'm just showing what we could do if we had learned a kernel like this one. What this kernel would do, it's a 7x7 kernel that's meant to look very comparable to that lesion of interest. What we could do is if we did the convolution of this with this, then we'd get this convolved output here. And you can see that this is a good size match for that feature of interest, and that's why we've got this very large dot located where that lesion is. Now what we can do is introduce a non-linearity, and in particular here the one I'm going to look at is called the rectified linear unit. And all you need to know about that is that it just sets any negative value in this feature map here, just sets any negatives to 0. It's like a thresholding operator. Because also, in fact, with these convolutions, we can also add an offset or a bias, which we can learn, which when used with a ReLU, will just change the threshold for the background subtraction. So if we do that ReLU, that rectified linear unit, set negatives to 0 after a given bias has been chosen, what we end up with is a nice feature map that only identifies that feature of interest, which for example is this lesion as indicated by our chosen filter in this example of how to do feature detection. So therefore you can see it's nicely picked out, that feature as emphasized in that red circle. Okay, now to build up complexity a bit, we could not just do one convolution kernel, we could do, for example, 2 convolution kernels. I'm showing 2 different examples here. And now when we put in one vector, one image, and run it through this single channel kernel, but we now have 2 of these kernels, 2 single channel 5x5 kernels. They're single channel because we've only got one single input. Then we're going to get 2 convolution outputs at the other side. So that's why I'm showing a 2 at the top of this, this rectangle, showing it's actually made up of 2 rectangles, 2 vectors, 2 images, which would look like this. For example, you can see this has picked out certain edge features, and this has picked out other edge-like features. Again, we could do an activation, a rectified linear unit, for example, setting negatives to 0, and we could see that we've drawn out various features here. Now I'm just giving kind of pre-chosen examples of kernels just to demonstrate the kind of thing that you can do with just a convolution kernel and with a background subtraction, which is achieved by a bias and an activation, which is what is going on in so-called convolutional neural networks, where we're using multiple kernels to deliver multiple feature maps. Then what we can do, for example, because if we kept on going with this, doing many different kernels, which remember we can learn, and we'll see why we'll learn them in a moment, what we'd end up with, of course, would be many feature maps, but what we often desire is one single endpoint output. And so that's why it's important to understand that we could use a single kernel, for example here, with 2 channels. So it's 2 channels in this kernel because we've got 2 inputs. And what this would do effectively is learn a kernel that would add together these 2 to deliver again one single vector output, which would be a 2D image. Just showing an example here. Of course, what we can do in general is tune those kernels to deliver an endpoint output that matches whatever our desired high quality reference might be. And so that's what I'm emphasizing here by fitting kernel parameters. So here it would be these 5x5 kernels, just 2 of them. And then even we could modify the weighting factors in this 2-channel 1x1 kernel. By learning those parameters via stochastic gradient descent, for example, with a loss function such as mean square error, then what we can do is have a learnable non-linear processing mapping that takes us from any input to any desired output within reason, whatever, if you like, the limitations are of the inductive prior that is our convolutional neural network. This is another example of a CNN. This is a nice piece of work published in 2021. In this case, the goal is not just to map from low count data to high count data, but in fact to map from a standard OSEM PET reconstructed image, to map from that to an anatomically guided MapEM regularized reconstruction, which is normally computationally very demanding to obtain compared to a standard clinically obtained OSEM reconstruction. So in this CNN, the input PET was first convolved with 15 different kernels, and you can see therefore we've got 15 different feature maps, and also the MR image was of course used because this is an MR guided reconstruction, so stands to reason that the CNN is going to need to make use of the MR input as well. This was convolved with 15 different kernels. And then these were concatenated, these two feature maps. So we've got 30 feature maps which go into a 30 channel 3x3x3 a set of 30 more kernels to give 30 more feature maps. And so we keep repeating this processing with these 30 channel 30 kernels in each one of these layers, convolutional layers, until at the very last layer we have a single kernel, 1x1x1 convolution kernel with 30 channels, which allows these feature maps to all be added together. And then finally, this will give an output. And the goal here was to train these parameters such that a regular OSEM reconstruction could match an anatomically guided MapEM reconstruction of higher count data as well. And here, effectively, they were learning 170,000 parameters for all of those convolution kernels. And they used 26 training data sets. That gives an idea of the amount of training data needed for this, drawn from 2 different radio tracers and from 2 different PET scanners. And they used the good old mean square error loss function. So not very sophisticated in terms of the objective function, but you can see it's delivering pretty good results with just mean square error loss. Now, furthermore, to add, they actually learned, in fact, the difference between the OSEM image and the desired output. So in other words, they learned what is it that you need to get here, what is the difference image that you need to find, which when added to that input will deliver the output. So if you like, this is a skip connection, which means just the residual was learned. And that's a pretty important methodology, because it means all of these convolutional layers can focus on finding the difference rather than having to deal with the overall global structures as well. The key benefit here was that rather than doing this reconstruction the slow way, which would normally be anywhere up to 100 plus minutes of CPU time, if you put this CNN into a GPU, this prediction of the anatomically guided reconstruction could be done in about a second. So many orders of magnitude faster. And you'll see next that it works very well when tested on unseen data. So this was for a different radio tracer, so not included in the training set. This is a fluorinating FET as the tracer here. They put in the OSEM reconstruction, the T1 weighted MR reconstruction, plugged it into their CNN, which had been trained with those other data sets with different radio tracers, 2 different scanners. This was from one of the scanners that was trained on, but didn't include one of the tracers that was used in the training sets. That's the key point here. This is a real challenge. And the prediction that they got was this. And when they compared it to the actual MapEM MR guided reconstruction, you can see they've got a very good agreement indeed. So very impressive results for generalization of a trained convolutional neural network. But what we're going to need to do next in order to do direct reconstruction is go a bit further with these CNNs. So really we're going to need at least something that can do a linear shift variant mapping in order to go from a sinogram to an image. I mean, I think you'll agree that you can't just find one single convolution kernel or lots of convolutions applied to a sinogram to take you directly to an image. You're going to struggle finding such a mapping. Okay, so let's take a look at how this basically works. I'm just going to give a kind of a basic introduction to this. Here again is a brain image with a lesion here, and as seen before, we can use some kind of pre-chosen kernel, though of course this will be learned according to the mapping in your training data that's required. You can see here that with this convolution kernel, we can see where that feature is, that lesion. So I've circled it here, and by using that kernel with a ReLU activation, we're ending up with just a feature map with that tumor or that lesion present. Now, imagine if we had 3 such lesions present in the image, then our convolution output would now nicely highlight those 3 lesions. And just to emphasize then that this feature map is showing us the spatial location of those features in the image. Now what we can do next is downsample by a process known as striding or by using max pooling, but the key thing is to downsample. What we can do is downsample in order to get a feature map which can represent collections of those relatively high resolution features. So the basic idea would be as follows. Downsampling can be achieved using strided convolution. So here this is exactly the same convolution process that we've been seeing before. It's just that it skips a pixel each time in the X and Y directions. And what that means is that the output feature map here has fewer spatial samples, but in fact is able to capture the entirety of that input image. So the receptive field of this output is quite large compared to its size and compared to the original input image. And this is where we get the concept of a hierarchy of features. So just like on the left-hand side here, we had 3 lesions and we had a feature detector showing where those 3 features are. Now we can use those 3 features together in a single kernel to try and identify groups of that feature. So that's why if we used a kernel a little bit like this one here, we'd be able to spot that pattern of features and identify itself as a single higher level feature. So that dot there is actually capturing a more complicated underlying pattern or feature in the original input. And so this concept can continue, whereby what we're doing here at this low level is, if you like, dealing with small features, which I'm here by analogy referring to as kind of atoms, if you like, small features. Now in reality, with CNN processing of images, these are often kind of edge detection units of different orientations, for example. And the point is that the next layer, the next stage of processing, you can start to be looking at features of those features. So if you like, with my atomic analogy here, that would be like saying, well, now let's group together the atoms into molecules. And once we've grouped things into molecules, we can do another feature detector and start recognizing collections of molecules to form materials, and then we can collect together materials to form objects. So this is just my simple analogy of how we can go through a whole cascade of feature detectors with downsampling, such that what we're doing is looking at higher and higher, more and more abstract level representations of the data. And typically what we do as we do that process, so here I'm just pointing out, in fact this analogy is actually quite useful, because you could imagine there are only about, I think about 100 or 109 or so different atoms in existence, but there are countless, many more molecules that could be made from those atoms, and still more materials. So the point to note here is that at this kind of first level, we have relatively few features, because there aren't that many atoms in existence, if you like. There aren't that many kind of edge feature detection kernels that can be found. And we can have high spatial sampling here, just like we would have high atomic level detail. But as we go up in the hierarchy, we actually need lower spatial sampling, and we achieve that by the downsampling, but we need more features, because there are more and more ways of combining those low-level atomic-like features. And so what I'm trying to convey here is that we end up with a hierarchy of features, increasing levels of abstraction of our data. And so what we end up with, if we keep going with this kind of processing, is that we end up with what's called a feature map. In fact, all of these are feature maps, but here, the feature map at the end of this chain of processing often has very low spatial dimensions, but very high feature dimensions. And if you like, what we've done is capture the salient information in our input, and we've just represented it in a feature space, a latent space instead. And often that can be used by object detection, CNNs. So we know that CNNs have done very well in object recognition tasks. But in the context of image reconstruction, once we've got that feature-based description of our data, we can then consider decoding that back into something that's of interest to us. So if this were an input sinogram, we could encode it into a feature domain and then decode it back into an image, which is why this approach is so crucial for understanding how to do reconstruction with a deep network. Okay, so there I'm taking that feature encoder And in fact, I'm showing it now explicitly as a whole series of feature maps. So here 32 means that each one of these is of 32 feature maps, and at each stage we've done a convolution as well as activation. And then as we're going down this pipeline here, this cascade of mappings, the spatial sampling is being reduced, and at the same time we're increasing the number of features. So in fact this diagram is a bit misleading. Really these rectangles should be getting fatter and fatter and fatter, because what we're doing is reducing the spatial sampling and increasing the number of features as we go. So once we've encoded our data, this is like doing an analysis. You could loosely view it as a kind of Fourier transform, a way of encoding your data into a different space that's useful to us. Once we've done that encoding, we can then decode it using a generator or a decoder or a synthesizer of our choice, by using, for example, even convolutional decoding. But at the same time, we're needing to do spatial upsampling here, and that's often just done by bilinear interpolation. Okay, so there I'm showing that we can encode information into a latent space and then decode it however we so choose. So this also gives us insight into another very important concept in image reconstruction, which is where we're going with these talks, that of the concept of perceptual loss. So what we can do is take an image and we can run it through an encoder network, and this one is the VGG network, which is a very well-known architecture of CNN. And what we can do is we can find a feature map, an encoded latent representation of that image. And this is useful because remember before we've been dealing with mean square error loss, where we just look at an endpoint image and compare that to the desired endpoint target. That mean square error is a useful metric for training our network, but in fact it's shown to not be as powerful as the case of when we use other measures of agreement between images, or in terms of desired reconstructions. So here I'm showing that another way of measuring the content of an image is not just the pixel level mean square error, but if we had some desired target, we could also encode that using a CNN, such as a VGG network, and we could get a feature map representation of our desired target. And then what you can do is come up with this idea of perceptual loss, where you look at the feature map, the latent space representation of our reconstruction, or you look at the latent space representation of our target, and you just compare those two, and we're saying, well, okay, we want the feature map, the feature representation of our reconstruction to match the feature representation of our desired target. And so that's where we get the idea of perceptual loss, which can often be used with mean square error to augment the loss function in deep learning for image reconstruction. So that's what I wanted to cover on CNNs, convolutional neural networks, and that's now setting us up nicely for moving towards direct deep learned reconstruction networks that can take us from sinograms to reconstructed images. So I'll start off with the example of the DeepPet architecture from Hagstrom et al., published in 2019. And so this uses that crucial concept of a convolutional encoder followed by a decoder. So what we have then is a sinogram input on the left-hand side, and this runs through a cascade, a series, a deep series of convolutional mappings. So you can see here use of 7x7 kernels, followed by 5x5, 3x3, and also at the same time ReLU activations being used between the layers here. And what's happening then, as we've seen before in our understanding of CNNs, is that as we decrease the spatial sampling, we simultaneously increase the number of features. So this is a typical example of a hierarchical feature representation where we're reducing the distribution of information spatially and converting it to a distribution of information in a feature space. So that's the convolutional encoder part of the network. And then what we have on the back end of that, once we've got the encoded latent space representation, we can then decode it back to a reconstructed image. Now, in their paper, in their method, they needed, no surprise, a huge amount of training data, which was obtained by simulation. They had 200,000 training data pairs in order to learn roughly 60 million parameters for all of those many kernels. But notice this is still quite a bit less than what would be needed if this was one huge, fully connected layer from a sinogram to a single image. So there is a saving of parameters through use of convolutional layers. They trained their method, as said, on simulated 2D PET data, and they demonstrated lower noise in terms of root mean square error measure compared to conventional ordered subsets EM reconstruction. And of course, given that it's a single architecture, input to output for inference of the reconstructed image, much faster than iterative OSEM reconstruction. Another example by Hu et al., published in 2021, was to take that convolutional encoder-decoder architecture, represented differently at the top here. To take that same architecture, they used the same parameterization of that with an encoder, decoder, and they're showing here in the latent space, they're doing transformations within that feature space representation. They didn't just leave it there, but they added on two crucial components, okay? So they used two extra networks in addition to the convolutional encoder-decoder network. And those two extra networks are basically in defining the loss function for how you get the output of the reconstruction network to agree with the desired high-quality reference, the target. And so they used a discriminator, and a discriminator network is typically used, or more well known to be used, in so-called GANs, or generative adversarial networks, where you can train up a discriminator to learn whether or not an image belongs to a particular set of images. So for example, in this context, we would have a whole training set of example desired output reference high quality reconstructions, and the discriminator can actually say, well, given a reconstructed image, it can learn to say whether or not that is a member of the high quality set. In other words, it actually thinks it belongs to the training set, it thinks it's an authentic high quality image, but it will learn whether to classify it as that or whether to classify it as something else. In other words, some poor quality generated reconstruction. If you like, you can call it a fake or an authentic output. And so the discriminator is actually trying to learn to catch out this generator network. This reconstruction network's trying to generate high quality images, but the discriminator is being trained to say whether or not this is actually a good reconstruction. And so these two are actually in opposition. This is trying to get better and better at generating realistic looking images, whereas the discriminator is trying to get better and better at figuring out whether it was actually a reconstructed image or whether it was an element of the training set. And so this discriminator is basically a way of enhancing the loss function. So in other words, not just doing a mean square error loss, but also including a discriminator-based adversarial loss as well. And so that can be shown to improve reconstructed image quality, because in fact the problem with the deep PET architecture when left by itself with mean square error, as shown in the previous slides, is that some of the images can be a little bit too smooth, which is what can happen with mean square error as the loss function. Not always, but that can be a tendency. A discriminator can be used to really sharpen up some of the images and make them look even more like high quality references. In addition, they didn't just leave it there, they also added on a perceptual loss. So I've already talked about perceptual loss, and here what they did was compare the perceptual loss of the high quality reference with the perceptual loss of their reconstruction, and in their loss function they want the perceptual losses, the perceptual feature maps to agree between the reference and the reconstruction. So it's yet another way of encouraging this generator, this convolutional encoder-decoder network, to generate high quality reconstructions. So taking a look at their results, you can see the ground truth is shown here. Here is an EM-based reconstruction with a smooth. This is a conventional post-reconstruction CNN denoiser. This is the deep PET reconstruction. And then this is their proposed DPIR, direct PET image reconstruction network, that uses not just mean square error, but also a discriminator and perceptual loss as well. And you can see that they've got more detail in their images compared to the others. So for example, compared to the EM plus Gaussian, in fact, you can probably see it even more clearly on this row here where they're showing low count data. The EM method is suffering from noise even after post smoothing. The CNN is doing fairly well, deep PET reasonably well, but their network is nicely recovering those details that are present in the true, and those details are not well recovered with the other reconstruction methods. So they definitely show advantages of upgrading the loss function away from mean square error and towards use of perceptual loss and a discriminator. This is a well-known architecture for MR-based reconstruction. So here in MR, they're using a single network to go from case-based data to an MR image. And here they are actually using fully connected layers. So these are pretty large mappings going from case space, which first of all has been flattened to, if you like, a tall vector, and running it through hyperbolic tan activations. And effectively, these fully connected layers, these two fully connected layers, are in effect learning a mapping from the Fourier domain, from the case space to the image domain. So this can be viewed as something like doing a Fourier transform. So that at this point here, they reshape their tall column vector into a 2D array and then follow it by a convolutional neural network in order to then basically do some nonlinear processing on that in order to represent that data in a high quality output form. And so they used 50,000 training data pairs in order to learn a colossal 800 million parameters for that very large network, just for 2D reconstruction. So they trained on MR brain data only, which yielded the best results compared to using different training sets, e.g. natural images from ImageNet. They demonstrated reduced noise and artifacts compared to conventional reconstruction. Obviously it's a fast reconstruction, and they also tried training it for PET data as well. The results in those early experiments weren't particularly convincing, but nonetheless a proof of principle of how to do reconstruction directly, whether for case-based data to MR images or even for sinograms to PET images. Now here is an example of a direct reconstruction network for computed tomography. Now this follows a more logical thought process whereby the architecture is being designed in accordance with what one might expect from a filtered back projection reconstruction. So these first few layers of the network are actually focused on doing denoising in the radial direction along an input sinogram, and then filling in any missing angles. So denoising and then populating missing angles if this is a sparsely filled sinogram with missing angles. So they train up this part of the network in isolation. So you can see here they used quite a large number of training pairs in order to train up these early layers, and then a large number of training pairs to populate, or rather to train up the angle filling layers. And then once they're trained with simulated data, they ended up doing end-to-end training of the entire network using hard-earned real data. And so again, just to break this down, these first stages are doing denoising and filling in of missing angles. And then we've got a lot of processing corresponding to doing the ramp filter, apodized ramp filter, so a noise compensated, noise suppressing filtering of the sinograms. And then we've got a back projection of each view. And so basically in back projection, you're summing things up in order to get a final endpoint reconstruction. So in their main real data, they ended up using 58 subjects for the training data for this ICT net. And the point here is this is a more interpretable direct reconstruction network where the various stages of the network have been associated with the usual stages in a reconstruction. So I refer you to an earlier part of the talk where I was talking about breaking filterback projection down into a cascade of operations, and that's exactly what they've done here to have a more informed, greater rationale for their reconstruction network. So let's briefly compare those various direct reconstruction networks. And so basically at the top here I've got some PET reconstruction networks, and you'll notice they've got huge numbers of parameters, but still not as many as what would have been necessary for a fully connected layer. And they're often dealing with only 2D reconstructions, so large number of parameters in the architecture, 2D reconstructions, and needing large numbers, tens to hundreds of thousands of training pairs. The MR reconstruction network, AutoMap, huge number of parameters, 800 million, 2D reconstructions, large number of training pairs. And then just at the bottom here, I've got the CT network. Now, because they had this more principled design of the network where they knew what each part of it was doing and then training it up in a sort of segmented fashion, they're getting away with far fewer parameters. Nonetheless, still 2D reconstruction, but relatively limited amounts of training data required. At the bottom here, I've also got a reference to another direct PET reconstruction network where they did manage to touch on 3D reconstructions using relatively small amounts of data, but still dealing with a large number of training parameters. So you get an idea here of what's going on with direct reconstruction methods. Sorry, that shouldn't say PET there. This is a comparison of direct methods. Take-home messages, typically 2D, large number of parameters, large amount of training data needed. We will now talk about how to go from sinograms to an image by unrolling iterative image reconstruction and embedding deep learning into the iterative reconstruction. So first of all though, why do it this way? Well, let's review what was going on with direct AI methods, direct deep learning methods. In their favor, they had few modeling assumptions. You're just basically left with the inductive prior of the architecture. The architecture can only express certain types of image, but that's a relatively small modeling assumption because these architectures are often very large and able to express many different images. They do use the raw data, and inference is very fast because once you've trained these up, you just put the sinograms in one side and out comes the reconstruction at the other end. However, they are very slow to train and they have very large training data needs, which is related to the size of the networks. Often 10 to 100 million plus parameters are required to define these architectures, and therefore correspondingly they also have high training data demands. As a negative, they do discard our knowledge of the system matrix of the imaging physics, and also they don't pay any attention to our knowledge of the statistics, the Poisson noise model. But of course, these architectures can learn the stats of the data, and they can also learn about the imaging physics when you give enough training examples. As mentioned, they're huge, and at the same time though, they've only really been mainly demonstrated for the most part for 2D reconstruction because of the sheer size of the architectures involved. And there's an open question about how well they generalize, because you need to basically ensure you're sampling sufficiently the domain of all the feasible radio tracer distributions or all the various objects that you might be imaging with your medical imaging scanner. So that then motivates the use of going back and using our system model that we would use in iterative image reconstruction. And because we're using our system model, we can sometimes refer to these approaches as physics-informed AI or deep learning, because we now use that system model, the imaging model that we have, and we can also include our Poisson noise model or our Gaussian noise model, whatever it might be. So Gaussian for MR data, Poisson for PET data and SPECT data. Of course, they, just like the direct methods, they do use raw data directly. And yet the key point being, unlike conventional iterative methods, which fit the parameters of the image to noisy data, with the machine learning paradigm, we are now making use of high quality reference data in order to learn the parameters for the machine learning networks. So also, because we're making use of our physics models, that means there's a much lower demand for training and for the number of parameters in these networks. And so these methods become practical for 3D image reconstruction and have much lower training data demands. Typically 10, 20, 30, 40 plus images are needed as examples. There are two main ways of embedding deep learning into iterative reconstruction, in other words, in a way that makes use of our physics models. One way would be to do very much what would be done for kernel EM, where you, for example, with kernel EM, you could, for example, use an MR image to define basis functions, and then use those basis functions to find coefficients of those basis functions via a reconstruction, and that'd be kernel EM. And so likewise, you could use a CNN model instead of a matrix of basis functions from a kernel method. You could likewise use a CNN model there as well. The approach I'll be focusing on will be using a CNN for the regularization for the actual prior in a deep learned unrolled iterative reconstruction. The point being here, the main difference between these two approaches, that approach 1 uses a CNN model for the image, whereas approach 2 uses it for the regularization, and that means that the deep learning is accounted for during the training of the overall model, with the deep learning embedded with the iterative reconstruction. Here are some examples of the methods, and I'll be focusing here on the FBSEM net example, but going over a general framework which largely captures what is going on for when we embed deep learning as the regularizer in iterative reconstruction. So quickly then, to review iterative reconstruction, for PET data we're dealing with a Poisson log likelihood. For MR data this would be the Gaussian log likelihood. We take the logarithm of the Poisson likelihood to get the Poisson log likelihood. So this is the distance measure, the data fidelity objective function that's used in PET imaging. Had this been a Gaussian for MR, for example, then this would reduce to a simple least squares objective function. Staying with the Poisson log likelihood for emission tomography, there it is again, the Poisson log likelihood, and we know that what we're doing when we have something like a log likelihood, we can say that we're looking at the gradient of the Poisson log likelihood in order to, given a current estimate of an image, we can get closer to a maximum likelihood estimate by adding on the gradient effectively. So just a reminder here that in our Poisson log likelihood model, we do have a model of the mean of the Poisson distributed data. So the Poisson distributed data are in a sinogram M, and our model of that data is given by AX, which is just the system matrix applied to our vector of image parameters. So we take the partial derivative of that Poisson log likelihood, and that follows quite simply to be this expression here, which is what we can call the Poisson log likelihood gradient image, and all it corresponds to is a forward projection of an image estimate, that's AX, estimate XK. We take the ratio between the measurement and the forward projection, back project that, and subtract off the so-called sensitivity image, back projection of ones, and that is the gradient of the Poisson log likelihood, and it's that gradient of the Poisson log likelihood that we add on to our current image to get a better estimate that's going to move us closer towards the maximum of the Poisson log likelihood. Now the algorithm that is used is a variation of this, and I've just motivated it via a gradient approach here, where in fact this gets scaled by the image value divided by the sensitivity image. And when you do that, you end up with a purely multiplicative algorithm, and this is the well-known MLEM method, or indeed it's very much what is used in an ordered subsets implementation for a lot of emission tomography reconstruction. So there is that algorithm again, shown at the top of this slide here. Basically forward project, ratio, back project, multiply to get the update obviously need to normalize by the sensitivity image. And what we can do to embed deep learning is first of all to view this, just like in other talks we've dealt with filterback projection and seeing that as a cascade of operators. We're going to do exactly the same thing now for the MLEM algorithm. We're going to view that as a cascade of operators. So this is like a deep network. So we've got some input initial image, we've got the measured sinogram going into each one of these EM updates, remembering the EM update is just given by that expression, these simple operations. And then we just have this series of EM updates. At any given iteration we have some reconstructed image, and we carry on for a finite number of iterations to get some last iteration. And this whole idea of unrolling iterative reconstruction was very much first proposed by Gregor and in fact Jan LeCun, one of the so-called godfathers of deep learning. So he was also the name behind the idea of unrolling iterative reconstruction back in 2010. Okay, so the point that I want to draw out here is that, of course, if we had high count data like this, then we might get a high quality reconstruction. But as we know, due to limited scan time or due to limited injected dose or indeed scan limitations, we often have very noisy sinogram data for PET, and therefore by the time we get to this last iteration, we end up with a noisy reconstruction. And so that is why conventionally with iterative reconstruction we use so-called regularized or MapEM methods to compensate for noise. So let's take a quick look at those. So this again at the top left is the Poisson log likelihood, but now with a penalty term. This is our prior, which penalizes images which we regard as not being very probable. So noisy images will give a large value of this energy term U. So U of X is basically a measure of image noise, if you like. Here is a common example of what's used for our regularizing prior. We basically say that if neighboring pixels are different, so here we take the difference between neighboring pixels and square them. If they're different, as they could well be in a noisy image, then that contributes to a growing sum of values that contributes to this so-called energy measure that is used in our prior. So the prior here would actually be exponential minus beta U of X, but because we've got the log of the Poisson likelihood, this is the log posterior, therefore we're just left with minus beta U of X. But anyway, this is just a familiar penalty term. So here on the left-hand side we have a data fidelity based update according to the Poisson log likelihood, and on the right-hand side we have an update that is in accordance with the energy term, in accordance with our prior. And then the overall update equation is basically a combination or a fusion of these two updates. So data fidelity update, Poisson log likelihood update, and then the update associated with the quadratic penalty. And so here is the data-based update, XEM, and then XSM for smoothed is the regularization-based update. And so we just join together those two updates to get an estimate which will be closer towards the maximum of the log posterior. So we could also unroll the MapEM algorithm as follows by considering again an initial image going into a MapEM update, which is given by these three steps as shown in those colored boxes. So we have a denoising step corresponding to this blue box, EM update, data fidelity based on the EM algorithm, and then a fusion, a joining together of the two updates as shown in that orange box. And we just keep on iterating, and eventually we end up with a map estimate, if indeed we continue for sufficient iterations. And so I have to say, with what we're going to be doing with the deep learned methods is we're going to be using a fixed number of updates, and so that doesn't necessarily mean that we are arriving at a true map estimate, because we may not be using sufficient iterations. So this result here is mathematically convenient, even though this objective, this penalized objective with this quadratic wasn't easy to solve. Nonetheless, it is mathematically convenient and so can arise with this straightforward update. But however, clearly this is unlikely to be an optimal measure of the regularizing potential or the regularizing energy function that we need to use. And so hence the question of can we use deep learning to learn that penalty function. Because just to add quickly, an alternative is to explicitly include weighting factors with this quadratic penalty that are based on differences in values in a MR image that is assumed to be registered with a PED image. And so, for example, if we use the method of Bauscher, these weights would be 1 or 0, sort of like a k nearest neighbors based approach. And this will now be a guided, smoothed update of the current estimate. And again, a data-based update, we fuse them together just like before. And so we're in a very similar situation. But now you can see that this image has certainly benefited from MR information. So we've got far more edges being preserved compared to the previous example. But it does leave the question of how much MR guidance should we use? And so again, that's where deep learning can come in, because we'd be able to learn just exactly how much of an MR image to use in order to appropriately regularize in order to match a high quality reference. Okay, so let's take that unrolled iterative algorithm, the MapEM framework, and we're just going to slightly modify that in order now to look at what we do in embedding deep learning. And this is very similar to what you've just seen. It's just that that denoising step now has just been kind of explicitly broken down into two components. One is actually a denoiser, and as we'll see, we'll be learning what that denoiser is. This will be a deep network, and then that is used as a fixed prior image for a number of MapEM updates where that prior image is simplistically used as a penalty. In other words, we don't want the database update to drift too far from that prior image that was obtained by denoising the previous estimate. So surprisingly, a number of unrolled iterative reconstruction methods fit within this quite straightforward framework. So in order to train up that deep network, that CNN typically for the denoiser, we're going to need to know what that endpoint iteration should look like. And so that's where, again, we can draw upon the idea of high quality reference data. Again, that's typically going to be high account data. For PET, longer acquisition times, or for MR, the analogy would be to use fully sampled case space, and this would be undersampled case space. And then the idea being that we would go through a number of EM updates, just conventional data fidelity based updates only, just seeking to maximize the Poisson log likelihood, which is safe to do for very high quality data. And then we get an endpoint iteration. And the point is, we can then use a loss function, a mean square error loss function, or indeed something more sophisticated than that, in order to compare the output from unrolled MapEM with deep learned denoisers included. We can compare that to the high quality reference through that loss function, and then we can back propagate according to the error in the mean square error loss. We can back propagate the corrections all the way through this cascade, this deep sequence of operations, which here are called modules, where each module has a deep denoiser as well as the EM update as shown. So here are 3 or 4 of the main methods for positron emission tomography for unrolling iterative reconstruction. On the top there's the method of Gong, which is MapEMNet. Here he used a UNet for the CNN, involving about 2 million parameters per CNN, and he actually used an iteration or module dependent network. Okay, so that means according to the number of iterations being used, you need to have more and more parameters in your architecture. He used mean square error, did manage it for 3D and with relatively low training needs, but then impressively did actually back propagate through all the layers, including the EM update. FBSEMNet basically used exactly the same CNN for all iterations and modules, therefore only 77,000 parameters needed. They were identical for all of the MapEM updates. Again, mean square error, end-to-end training, 35 training pairs, although in this paper we did not back propagate through the EM update. Then there's BCDNet, or in fact more accurately the iterative neural network method, where they did use an iteration or module dependent network. It's like a kind of a convolutional encoder-decoder approach with a relatively limited number of parameters. Again, depending on, I think it's 4,000 parameters per network, and then 10 main modules of update gives them, for example, about 40,000 parameters. But it'll depend on how many iterations you unroll as to how many parameters are involved. Again, 3D reconstruction, quite modest training data requirements, and the training was done at the module level only, and so no need to back propagate through the whole cascade of the network. And in fact, just to point out for FBSEM Net, there was a paper recently in 2021 where iteration-dependent targets were used, and then also sequential training of each module was used, very much inspired by the iterative neural network approach, because that's quite a practical method for training the CNN at each and every update without back-propagating all the way through the entire unrolled network. So let's take a closer look at FBSEM Net. So again, this is like the MapEM update framework. We've got the data-based update, EM update, and then we've got a deep network for the regularizing prior here. And let's take a look at what is going on clearly here. So we've got the Poisson log likelihood shown here. And again, we've got the regularization term here based on a prior or a penalty U of X. And we're trying to find an X that will maximize that objective function, the log posterior. So given any current image estimate xn, what we can do first of all is do a gradient descent using the gradient of this regularizing prior. Now the point here is that we're not making any claims as to what that is. Before we assumed it was a quadratic penalty, and we had the solution that we saw before via De Piero. Here we're not going to make any claims about it at all, and we're just going to say, well, there is some smoothed update, some denoised update that arises from a gradient descent. So here we've got a step size with a regularizing hyperparameter beta controlling the strength of the penalty applied to the gradient of that penalty function evaluated at our current image estimate. So this is gradient descent, and what we're going to do is just say, well, actually, let's do all of that just with a deep network. So here for FBSEM Net, these architectures were identical for each and every module. So we're just replacing that whole step with just one network applied to a current estimate xn. That's the learned regularizer. And again, that is learned by looking at what goes in on one side. Obviously, we've got the sinogram being fed in at every EM update. We get some output here, and then we just compare that output to the high-quality reference using a mean square error loss function, and then back propagate from there. Okay, so once we've got the gradient descent update based on the regularizing prior, we're now in a position to do a proximity operator where we're saying let's get our next update based on finding the X that maximizes the Poisson log likelihood, but with a penalty if that X drifts too far from the regularized update, from the gradient descent update according to the prior. So that's why I'm calling this Poisson log likelihood with a proximity requirement for the denoised update. So this is known as the proximity operator. And what we do to achieve the solution to this, the next update, which is based on maximizing this expression, what we do, as we always do in fact, is use, when we're using the EM update, we end up using a complete data log likelihood. That's the conditional expectation of the complete data log likelihood. We use that as a surrogate for the actual Poisson log likelihood using so-called incomplete data, the actual measured data M. Instead, we use the complete data log likelihood because we can use that as a surrogate function which we can maximize in one single step, and that's what we get with the expectation maximization update, because that's maximizing the complete data Poisson log likelihood. So that's the familiar EM algorithm. And because now we need to also account for that very straightforward image-based penalty, if you like, that's element by element, pixel by pixel, voxel by voxel, quadratic penalty, where we're saying X mustn't be too different from that, then we can use this very simple update. Again, this can be found via De Piero, or in fact Levitt and Herman even earlier on had a very similar expression to this, where the next update is given by the data-based update in combination as the data XEM update in combination with the regularized update. So their XReg actually is referring to the smoothed update XSM. Okay, so let's see how it does. This is with 3D simulated data. We've got MR reference here, as well as a high quality PET reference. This is simulated data. For 10 to the 10 counts, this is the reconstruction, so that's a huge number of counts. And then with 100 times fewer counts, so 10 to the 8, we have the OSEM reconstruction, and then the OSEM reconstruction with PSF modeling included. Then if we do a MapEM with MR guidance, we get this result here. And then on the right hand side, I'm showing the outcome of using FBSEM net. And you can see the image quality improvement compared to MapEM and compared to OSEM is actually very favorable indeed. Although in fact the conventional UNet, which is just a post-reconstruction CNN, a UNet applied post-reconstruction, is actually also doing very well, but this doesn't revisit the data, whereas this one does. And so it'd be interesting to look at cases of tests for generalization to show that this one can benefit from revisiting the sinogram data at every single iterative update. Tested on real FDG data, these are the results that we see. This is now 30 minutes of data as a reference, and then our reconstructions are on the right hand side here. OSEM for only 2 minutes of data, suffering noise amplification. Post-reconstruction, a UNet doing very well indeed, and then again our FBSEM net also holding up very well and showing significant improvements compared to the conventional OSEM. So I just want to touch on another thing that can be improved upon here, is to use iteration-dependent networks along with iteration-dependent loss functions and targets. So here now, instead of just going with the last endpoint training here, so this is initial image going through all of those different modules, and then we get a reconstructed image out the other side. Normally we'd just do the mean square error loss between this reconstruction and then a high quality conventional OSEM reconstruction, giving this result here. And normally we'd only do those, do the loss function on those two and then back propagate to update parameters. Here though, you can see we've actually got the mean square error loss applied at every module. So here we use the high quality reference at every single update and use that to inform the learning process of the networks. And what that will do really is stop the method from learning to do all the hard work at the last module, which is in fact what can happen. Whereas here, this imposes the requirement that we expect a nice gentle progression towards the high quality final endpoint image. And so this was a method published in 2021. These are the results with the method. First of all, just giving reference points, OSEM with and without PSF modeling. And then with the iteration-dependent targets and with sequential training, this is the result obtained here, which is being compared with the iterative neural network implemented independently here with two different architectures. And we get quite satisfactory results here compared to the high-quality reference. Okay, so just to summarize then at this stage, so with conventional reconstruction, we've seen from the very beginning that it's fitting an image to noisy data, and so normally we need to regularize, but those regularization methods are too simplified, for example, just based on quadratics, and we don't know how strong to make those priors. Whereas machine learning, which can be done in two main ways, instead of mapping instead of fitting to noisy data, instead seeks to map noisy data to a high quality reference. You can either do that directly with a large network, or you can do it via unrolled methods like I've just been talking about, where you embed deep learning into the cascade of updates. I'd just like to finish by acknowledging my co-authors on a deep learning review article that I wrote recently. So thank you to Guillaume Corder, Abifaz Moranian, Casper Costa-Lewis, Sam Ellis and Julia Schnabel. And finally, just to point you again to an article I wrote with Georg Schramm entitled Artificial Intelligence for PET Image Reconstruction, published recently in J&M. Thanks again for listening.